So I was saying that there is this new, there is this seminar series that is called Seed Seminar on Mathematics and Physics, and it was already. It's not completely new. I mean, there were some events online in the past years, but now we moved to some in-person event, and this is the first one. So, this is the first one. So you can see the program on that website, and it is so there are there will be also some Zoom talks. So please have a look at the program. So this first thematic period, which will last for a trimester, it is. It is about conformal filters and sphere packing. So it is really our pleasure to have Dalimil Mazáč from Saclay, who is talking about the geometric applications of the conformal bootstrap.
Thanks a lot. Before I start, can we just make sure people on Zoom can hear it? Yeah, anybody respond? Yes. Okay, great. Yeah, thank you. Thanks a lot for coming. Thanks a lot for the introduction. And yeah, I can turn this off. Perfect. It's all this. I think the live situation should be good. Okay, yeah, great. Thank you. Thanks for having me. I'll tell you something about some work I've been doing over the last few years with some great collaborators on the geometric applications of the conformal bootstrap. And the idea is that there is this method in theoretical physics called the conformal bootstrap, which is usually used to constrain and study conformal field theories, which are maybe somewhat esoteric but very interesting objects. But today I'm going to use the same method to not talk about conformal field theories, but rather I will see how it leads to some new rigorous and rather surprisingly powerful results in mathematics. So I'll apply it to some rather familiar mathematical objects, which are not conformal field theories, and see how it rigorously applies and can teach us something new. So it won't be important whether you know or don't know what conformal bootstrap is. I will not really explain what a conformal bootstrap is. Maybe towards the end I may, but I'll try to make the talk self-contained, just focusing on these mathematical applications. And okay, so let's jump right in. The main application, or the main focus of the talk, is going to be on the properties of two-dimensional hyperbolic surfaces or two-dimensional hyperbolic orbifolds. So let me quickly review what they are. So this is that setting of 2D hyperbolic geometry, which starts from the upper half plane. So that's, by the way, is there some pointer or something? Oh, I'm sure. Okay, then. Oh, no worries. I will just point with my fingers sometimes. So there is a upper half plane shown here, two-dimensional surface with this Riemannian metric, dx squared plus dy squared over y squared. And the most important fact about it for my talk is that its group of isometries is this very nice group PSL2R. So how does PSL2R act? Well, it's a group of 2x2 matrices, basically. A, B, C, D are 4 real numbers, and it acts by Möbius transformation. So AZ plus B over CZ plus D is an isometry of that metric, and it's all the orientation preserving isometries of that metric. And now, if you want to build a hyperbolic surface, so surface with a metric of constant negative curvature -1, such as this one, you just need to take a discrete subgroup of PSL2R. So gamma is a discrete subgroup of PSL2R, and then the quotient of the upper half plane by that group gives you an orbifold, or a surface or an orbifold. I'm going to, okay, there are some technical assumptions here. I'm going to assume that the quotient has a finite volume. So, this thing doesn't have a finite volume. So the volume sort of goes to infinity as you go to the boundary. But you can choose gamma such that you quotient it out at the infinite volume, and you just get a quotient of finite volume. Now, if gamma only has so-called hyperbolic elements, then the result is a compact surface. So it has no boundary. Basically, you completely get rid of the boundary by the quotienting. And if gamma also has elliptic elements, then the quotient may not be smooth. It can have these orbifold points, which come from the fixed points of the elliptic elements. So elliptic elements are just elements of PSL2R that have fixed points inside the upper half plane.
Sorry,
yeah. Yeah.
So we normally say 1D conformal group is SL2R. The P. How should I think of it in the physics?
It's. I mean, the 1D conformal group is PSL2R. It is not SL2R because it acts like this, and you can see that the matrices which are proportional to identity act trivially, because if the matrix, so the only multiples of identity in SL2R is plus and minus identity.
Right.
And you can see that if you choose minus identity, it's just -1, -1, 0, 0, and that keeps Z unchanged, so it doesn't really act. So it's the 1D conformal group is PSL2R.
So it's there is situation that it has infinite volume.
Yes.
So when does it have finite volume for this critical?
For example, SL2Z is a very famous example. It has a finite volume.
Okay.
It's non-compact. So the fundamental domain is this keyhole domain. It's non-compact, but it has a finite volume. But there are also examples that are compact. Well, no, if it's compact, it has a finite volume. But
It's
Fuchsian groups. Okay, well, actually, here are some compact examples. So the most important example are triangles, which arise by taking three geodesics in the upper half plane. So they're just semicircles, and taking the group to be generated by the rotations around the sort of the vertices of the triangle by some appropriate angles. And then the fundamental domain for such a group will consist of two adjacent triangles. So it's because you're not just using reflections, you're only using rotations, not reflections. That's why you need two adjacent triangles. And the quotient looks like kind of like this. So it's topologically a sphere, but it has three orbifold points. So there are 3 points where it's not smooth, where the total angle is some integer, 2 pi over some integer. And you can classify, so these things are classified by these triples of integers, k1, k2, k3, subject to the constraint that that the total area given by this formula is less than 1. Sorry, the area must be positive, which implies that this sum needs to be less than 1. That's an exercise in hyperbolic geometry. And then you can check that the initial question is if there is an element of the smallest area, and there is, and it's the orbifold with degrees 2, 3, and 7. This is going to be an important orbifold that will play some role later on. But all of these are just topological spheres with some non-trivial orbifold points. Okay, are there any questions so far? Clear? And okay, let's look at a smooth example with no orbifold points. So these have to necessarily start at least genus 2. There are no smooth things which are hyperbolic for smaller genus. At genus 2, there is a 6-dimensional moduli space of these 3 complex dimensional, 6 real dimensional moduli space. And there are some very interesting points in this moduli space of hyperbolic metrics. The most symmetric point is the Boza surface. So it has the larger group of isometries, some finite group, the group of isometries, GL2 2x2 matrices over the field of 3 elements, group of order 48. And here's a picture of, well, here's like kind of a cartoon, what the surface looks like, and here's what it really looks like. Because this is the hyperbolic disk, and the gray area is a fundamental domain of the, and you can tile it with 2, 3, 8 triangles. So triangles with degrees pi over 2, pi over 3, pi over 8. It's a very nice symmetric surface. And more generally, it will be useful to introduce an invariant of these surfaces, which is the topological type, which just consists of the genus and the orders of the orbifold points. Okay, so if they are smooth, the topological type is just the genus, but more generally, we also want to keep track of the orders of the orbifold points. And this topological type is the same thing as the isomorphism type of gamma. Right? So there could be a moduli space of surfaces, which means that there are different ways to embed the same group into PSL2R. Okay, that's what it means to have a moduli space. But the topological type doesn't keep track of the embedding of the group into PSL2R, but just of the group itself, of the isomorphism type of the group. Yeah, does this? It's okay. Okay, and the quantities that we'll care about in the talk is the Laplacian spectrum of that surface or orbifolds. So let's review what the Laplacian is. It's a quadratic differential operator on the upper half plane. It takes the explicit form, and we want to solve the Laplace equation. But we don't want to solve the Laplace equation on the upper half plane, but rather on the quotient, which means we should solve the Laplace equation on the upper half plane subject to an invariance of the eigenfunctions that are invariant under every element of the group gamma. Now this is a eigen problem whose spectrum is discrete for compact surfaces. So some discrete spectrum, and we just lost the thank you. Perfect. Okay, so we have a Laplacian on the hyperbolic surface. It's a compact, so the spectrum is discrete, and it's a very interesting mathematical problem. And there are in fact no closed expressions for these eigenvalues in general. So for example, on the sphere, you can give a closed form solution for the eigenvalues. You cannot do it here for any compact surface. For arithmetic, actually, let me just make another comment. There's some interesting connection to chaos. So classically, this is like a quantization of the classical problem of a motion of a free particle on a hyperbolic surface, which is classical chaotic. And you can expect some imprints of this chaoticity in this quantum Schrödinger equation problem. And in fact, there's some eigenvalue repulsion and so on, which is expected for chaotic systems. But I won't really talk about it too much today. I'll talk about the lambda 1. So the first positive eigenvalue, which is also very interesting. So for example, for arithmetic surfaces, which have some number theoretic significance, there is an important conjecture due to Selberg, Selberg 1/4 conjecture, which says that for a specific class of these surfaces called congruent surfaces, the first eigenvalue is always lower bounded by a quarter. And this is a conjecture that is basically a special case of the Langlands program, and if you can solve it, you'll probably win lots of money or something like that. Anyway, it's a very interesting conjecture, and I won't solve it certainly today, but I will introduce some new method for studying this spectral gap, the first eigenvalue lambda 1, but not really for proving lower bounds, which is what the Selberg quarter conjecture wants, but I'll find some new upper bounds on lambda 1 on a given topological type of a surface. Okay, so here are the main results that we proved, and I really do mean that we proved. Like, we are physicists, but we actually took great care of being very rigorous in this paper and prove it to mathematical standard. So the first part of the theorem, or the two parts of the theorem, and they are each an upper bound on the eigenvalue of some genus. So at genus 2 there is a moduli space, and the first eigenvalue varies over the moduli space. You may wonder, where is it maximized? What is its maximum? And it's a hard problem. It's a 6-dimensional moduli space, so you can't just solve the Laplace equation at every point of the moduli space and numerically and find what the eigenvalue is. So which is why these results are interesting. And the result says that, for example, in genus 2, there is an upper bound, which is some rational number that you can approximate like that, 3.83888977. And then you can compare it with some genus 2 surfaces. And you'll find that one of these surfaces actually has an eigenvalue that's very close to it. So it's 3.83888729. So luckily it's below the bound, which it should be because it's an upper bound. And upper bound is probably saturated. Well, it may be saturated by the surface. Okay, so the eigenvalue somehow varies. It goes to 0 at infinite sort of at some degeneration points, and there is a special very symmetric point where it's almost saturated. And our result.
If there were a lower bound, I think it's numerical. Well, you can think about maybe some rational uncertainty.
Yeah. I think this estimate, you mean, for the Bose, that's what you're asking about? Yeah, I think this is some non-rigorous estimate, but you can do some more rigorous estimate, which will give you a kind of a rigorous window for what the eigenvalue is. We didn't try to do it here, but I think all of these digits are probably rigorously correct for that surface.
So that 1/4 is for lambda 0.
One quarter.
Lower bound. So in the previous.
The Zilbert, so the Zilbert 1/4, it has a bit of a different flavor because it's a lower bound on all congruent surfaces. So there is a class of surfaces which have various genera, and they arise from number theory. And in spite of their genus going to infinity, the lambda one can never go to 0. And it's conjecture that actually never gets below 1/4. So it's a very surprising result because genus goes to infinity, the volume kind of goes to infinity as well. So you would expect that the lambda one will become very small, but that's why it's a very striking conjecture.
So why don't we care of lambda 0?
Lambda 0 is always 0. It's the constant function for compact surfaces. Yeah.
Okay.
And there's a similar result that we have derived for genus 3, which is an upper bound again, 2.678. Again, it's some rational number so this is some rigorous rational number. And there is a very special surface, which is actually a Herbert surface. So it's got a very large isometric group with eigenvalue 2.6779. Again, it's just a little bit below. And again, we improved on the previous best bound by a few decimal places. Here we actually improved by quite a bit, and we got very close to the actual surface. But maybe more interesting than the results is the method. And also before I talked about the method, let me also tell you about another result that we derived. So that's the spectrum of the spectrum, or spectrum of lambda 1. So again, this conjecture of Zilbert that I already said is that if gamma is a congruent subgroup of SL2Z, then lambda 1 is a quarter, which you can also state equivalently as saying that if the surface X ranges over congruence orbifolds, then the image of this map that takes the surface to its spectral gap lambda 1 is just the set 1/4. You cannot get anything below or anything above. And okay, so that's a question about congruent surfaces. But you can ask the question about all surfaces. So what is the image of this map when X ranges over all the orbifolds? And we gave an answer in our paper, which is more or less rigorously proved up to certain finer details that I may tell you about later. But here's the answer. So the answer is that lambda 1 can take this set of values shown in blue. There's a maximal element, which is 44.88835, which actually corresponds to the 237 triangle. Then there's 2 more discrete points corresponding to other types of triangles, 245, 238, and 334. There's actually 2 different triangles, one covering of the other one sitting here. And then there's a continuum starting at 15.79, going all the way to 0, which is where you find the first topological type that has modulus. So the first one that has a modulus is the sphere 4 punctures, right? Sphere 4 punctures has one complex modulus because you can take the punctures pairwise away from each other. And by doing that, you create a long throat such that the lambda 1 goes to 0. Like there's this eigenfunction that varies very slowly along that long direction, which allows you to reach all the way to 0. Okay, so the main point maybe of my talk today is to explain how we use the conformal bootstrap to prove this result. Oh, by the way, are there any questions about the results? Like what it is that we actually proved?
Is it a tiny window and the higher? Yeah, some tiny window with some very tight upper bound and lower bound.
Oh, this is just a point. This is rigorously just a point.
So this is already known.
This is known thanks to our work, which I will explain.
I see. So before it is not even known.
It seems like people didn't really ask this question, but what is the, well, maybe they did, but yeah, it wasn't really known what is the possible set of lambda ones arising in all hyperbolic surfaces.
So if there are higher lambda ones beyond the most right one.
No. This is it. There's no lambda ones. It's like in CFTs. It's a result that would show there is no CFT whose spectral gap is above, say, 44. That's a small type of result. So it's actually a very interesting question about CFTs, right? Are there CFTs whose spectral gaps, whose first delta one is large? In this case, you can show that there's a universal upper bound which is 44.888, nothing above it.
And the accuracy part of known here.
Yeah, these points actually exist here. Yeah. But they are not CFTs. They are like CFT analogs. So it doesn't.
Just a quick question. So these numbers are upper bound for exact numbers that.
Well,
so in a sense, is this really a point?
This number is defined to be the lambda one of this surface. So in that sense, it's a unique number, which is probably some transcendental number with an infinite decimal expansion. And our method of proof is not by proving an upper and lower bound. Okay, let me just say, the idea is that the method allows us to prove upper bounds on given topological type. So the way we do it is that first we prove a universal upper bound on all the topological types. So that shows that there can be nothing to the right.
Yes.
And then we prove an upper bound on all topological types except for this one. And that upper bound is somewhere here. So that tells you that the only thing that can be between here and infinity is a single surface, and it's this one. So it's
okay. I understand. Thank you.
Sorry, just to like I understood. So you said like about this chaotic motion of the particle.
Mhm.
So you're not talking about like ADS. You see an ADS, you wouldn't be chaotic. But you're saying in these orbifolds.
yeah. That's right. Yeah.
So there's some orbifolds where it's not
Yeah.
chaotic.
Yes. There's precisely the arithmetic ones where it's not, well, then you get into some subtleties of defining what chaos exactly means. So there are these special arithmetic ones for which the eigenvalues don't exhibit the repulsion, for example. So yeah. But generically, it's supposed to be a feature, this eigenvalue repulsion. Okay, so let me finally tell you what the method is. So the idea is that for a given topological type, we can fix the spectrum of the holomorphic discrete series in this Hilbert space. And I'll explain all these things a bit better later. But basically, these are the holomorphic modular forms. And the spectrum of holomorphic modular forms is very rigid. It only depends on the topology. It doesn't depend on where you are in the moduli space at a given topology. And once you do that, you consider an integral basically over the surface or over some bundle over the surface of a quadruple product of holomorphic forms and their conjugates. Okay, so you consider that thing. And then you do two spectral decompositions. You kind of take the product of two of them and you apply the spectral theorem for L2, and you find that there is just contribution from discrete series representations for product of two holomorphic forms. And then in the other channel, so kind of taking a product of F2 and F3 bar, there's a similar story, but now you only find principal series, and this is where the Laplace eigenfunctions live. So instead of on one side, you have only holomorphic forms, which are very rigid. They give you a lot of control. On the other side, you have these very interesting Laplace eigenvalues that you want to study. So what you end up with is an infinite collection of identities, which equate an infinite sum over holomorphic forms to an infinite sum over Laplace eigenfunctions, and which has some positivity properties. So basically, you have some positive numbers times polynomials that you can control, and then you can do some interesting linear programming in the space of these identities to get optimized upper bounds on lambda one. Which okay, and then this is just a sketch, but I'll spend the rest of the talk explaining the steps in more detail. But if you want to ask now about something, that's fine also. Okay, let me just say there's been some related work. So first, Bonifacio Hinterblicher had a similar idea in a more general context of Einstein manifolds. Then James Bonifacio first did the hyperbolic manifolds. but without doing any representation theory. So it was all a bit kind of, I mean, it was very good, very nice, but a bit ad hoc. And what we did with Peter, Kravchuk, and Schroeder-Pal was to phrase everything in a representation theoretic setting of PSL2R, which also manifests the relation to conformal bootstrap. Okay, we systematize the ideas using representation theory. And also, finally, also Borg and Bram-Petry. So Bram is actually here in Paris, I think at Sorbonne, mathematician. They applied linear programming not to these quadruple overlaps, but to Zellberg trace formula to find some interesting upper bounds and spectral gaps of hyperbolic surfaces. There's a typo. Okay, but now let's jump into the actual method. So the main object, so that you want to think about when you think about hyperbolic surfaces, is not the surface itself, but rather a circle bundle over the surface, which is also known as the unit normal bundle, I think. Well, it's basically the surface with a circle attached everywhere. And you should think of the circle as a copy of the maximal compact group of PSL2R. So the PSL2R has a one-dimensional compact subgroup, which is SO2. And when you quotient the PSL2R by the SO2, you just get upper half plane, right? Because upper half plane, a point in the upper half plane is stabilized by rotation by SO2. So by the orbit stabilizer theorem, you get upper half plane as a quotient G mod K. Now, if you want to get the surface, you should quotient the upper half plane by discrete group gamma. So you get sort of double-sided quotient. So this is three-dimensional, this is one-dimensional. So this is two-dimensional, and this is also two-dimensional. It's just a discrete group. So double-sided quotient is the surface. But there's a better object to think about, which is this one. So it's the one where you don't quotient by K. You just quotient the group by the gamma. And you get a three-dimensional manifold, G mod gamma, which carries a right translation action by G. So that's why it's nice, because this one doesn't have any symmetry. I mean, you've gotten rid of both the left and right translation action by quotienting on the left and on the right. But here you keep the right translation action, but you also keep track of the group gamma. So that's the point. Okay, so this is a very essential point. If anyone wants to ask, you can ask. Okay, and why is it essential? Well, because now we can think about a Hilbert space of L2 functions on this G mod gamma, and because we have an action by right translation, we get a unitary representation of PSL2R, and that's something that we really like in the bootstrap. We really like to have a unitary representation of the conformal group. So we have this space. The group acts on functions. So it's a space of functions on G mod gamma. Group acts by right translation. It's unitary because, well, there's the measure is just the Haar measure on PSL2R. So it's preserved by this action. And now, what is the interpretation of these functions? So one way to understand it is how you decompose this Hilbert space as a think of it just as a representation of the subgroup of this SO2. SO2 representations, they're just labeled by integers. They kind of tell you this is the momentum around the circle. It's extra circle. So it's the momentum is an integer. And when n is 0, that means that the function is invariant under SO2. So it's just a function on the surface itself. So in particular, this V0 is just the space of functions on the surface. But there are other functions in here which are not in here, which are like non-trivial Kaluza-Klein sort of functions in here, and they correspond to n form. So if you have some function that has that looks like e to the ixn around that circle, that will descend to a function on the surface which transforms under the group gamma with some extra prefactor. So it basically transforms like a modular form. And the generators of PSL2R, they're like ladder operators which map you between different values of this integer momentum n. I mean, if you haven't seen this, then it may be a bit hard to understand. But basically, you should think of this as an upgrade of the space of functions on the surface. Like it's a space of functions together with a space of some forms and other things in a way which makes it into a unit representation of PSL2R, which the space of functions itself is not. Okay, and then you
just saying why the space of functions is not unit representation.
Well, because SL2R doesn't act on the surface.
Ah, sorry.
Yeah, SL2R only acts on this bigger thing.
Yeah. Sorry.
Yeah. No, it's a good question. It's exactly what I should have said actually. Yeah, SL2R doesn't act on the surface because you're doing the surface is this double quotient. So there's no where it can act. It acts here. Okay, and once you have a unitary representation of a nice non-compact semi-simple Lie group like PSL2R, the first thing you want to do is decompose it into irreducibles, which is also something that we always do in the conformal bootstrap when we take the Hilbert space of states and decompose it into irreducible representations of the conformal group. And here is what you find in this case. So you find the trivial representation, the one-dimensional C, which is just the constant functions. Right? It's functions that don't depend on where you are on G mod gamma. And then you find a discrete direct sum of very infinite dimensional representation. So all of these are infinite dimensional besides the constant. There are the principal series and a discrete series. And what do they mean? Well, principal and complementary series, but they're almost the same for our purposes. So that these ones correspond to Laplace eigenfunction with eigenvalue lambda. So abstractly as a representation, this is labeled by some number lambda, which is basically the quadratic Casimir. But concretely, in this case, it's realized as Laplace eigenfunctions. So more precisely, this is an infinite dimensional representation, the P lambda, which has a one-dimensional component inside V0. Maybe I wrote, oh yeah, here it is. So P lambda is infinite dimensional, and the ladder operators increase and decrease n, but when you're at V0, it's just a function on the surface, and the Casimir acts like a Laplacian with eigenvalue lambda. So that's how. So there's a one-to-one correspondence between Laplace eigenfunctions and occurrences of P in this direct sum. And similarly, for the discrete series, there is such a correspondence with holomorphic modular forms. And so these representations are also infinite dimensional, but they are lowest weight, unlike the principal series. And the lowest weight vector, which is this one, so it's annihilated by lambda 1, by L1, sorry, it is a holomorphic thing because L1 acts like a anti-holomorphic derivative. Okay. And the label n tells you what is the weight of that modular form. Similarly, there is an anti-holomorphic discrete series, which are just complex conjugates. So these representations always come in complex conjugate pairs in the direct sum because of complex multiplication, right? Complex conjugation. You can always complex conjugate things, and D is not real, but D plus D bar is real.
So the Laplace eigenfunction, so it is not a complete basis of the L2 here.
The Laplace eigenfunctions is a complete basis for L2 of x. So we are coming back again to this. So L2 of x, sorry, or maybe I can write here. So here is a picture of the representations. P of lambda. Oh, no one can see that. If I do this on a shrinkage. Yeah, so the P looks kind of like that. No, these are the values of n of the momentum around the circle S1. This is n equals 0, and ladder operators move you like that. And the D and D bar look like that. They always start either above n0 or below n0 and go. So D goes up, D bar goes down. But if you only look at n equals 0, then only the P's contribute. Right? So if you want to decompose the space of functions on the surface, that's the same thing as n equal to 0, and you just need a principal series. But once you want to decompose other n subspaces, you also need a D and D bar. Yeah, maybe this is. Yeah, we create. It's just, again, the basic reason is that we are not decomposing the space of function on the surface, but the space of functions on this circle bundle over the surface, which is bigger. So that's why we need other things. Yeah.
So just so the d lambda part function, the eigenfunction doesn't are not modular functions. The functions that are in d lambda.
What do you mean modular function? You mean on the previous, like this?
In the sense of having this equation,
No. They are with n equals 0. So they are just invariant on the nose.
Okay.
Yeah. So n equals 0. So this is not there, just invariant, and all of the other things they are similar, but with this extra prefactor. But they're not necessarily holomorphic. They're only holomorphic if they are the lowest weight vector. Okay. Okay, so now we are in a situation that we normally have in a conformal bootstrap with your Hilbert space. It has a spectrum. In this case, the spectrum corresponds to solving the Laplace equation. So it's a nice non-trivial spectrum. Maybe it's chaotic at high energy sometimes. But we want to know, what kind of spectra can arise from this construction. Can we just pick a random spectrum? There will always be a surface that has that spectrum. No, and that's what the bootstrap does. Bootstrap can tell you what kind of spectra actually can occur, and more precisely, what we do in our work is that we first fix the topology. The topology fixes the red part, the discrete series, but it doesn't fix the blue part, the principal series. So everywhere on the moduli space, the same topology, these don't change, the spectrum of these don't change, but the spectrum of these does evolve. And okay, the multiplicity of a given dn is fixed by the topology, by the genus and the degrees of the orbifold points. So we can focus on specific topology just by making some simple spectral assumptions about the spectrum of the d's. And then we can use it to constrain the spectrum of the lambdas by using an algebra, which is just the algebra of multiplication. So you can multiply two smooth functions. This is like the OP for a conformal field theory. You multiply two functions together, and this respects the invariance under PSL2R. Both sides. If you act with PSL2R on F1 and on F2, there's the same, and multiply them is the same thing as first multiplying them and then acting. So it's an OP that respects conformal invariance, and eventually it leads to these bounds. Okay, now it becomes a bit closer to conformal field theory. So you can kind of make the connection to CFT manifest by defining local operators from holomorphic modulo forms. So we start with modulo form of weight 2n, and we act on it with this space-time translation e to the w l minus 1. So and this defines this O of w, which you should think of as a function in this Hilbert space. It's a function on G mod gamma, which depends on w. So w is just a parameter for now. Okay, it has some properties which maybe are not so important. Maybe something that CFT people will recognize is that the generators PSL2R act on O in the same way as conformal generators act on local operators. This is the usual sort of truncation of Virasoro action to the global part. And there's a similar construction that you can do for the complex conjugate module forms. And now when you do that, you can define correlation functions, which you define by first taking a bunch of smooth functions in G mod gamma and define their correlation to be just an integral of their product. So kind of almost exactly like what we do in CFTs. So here's the definition. And because the measure is G invariant, also these correlation functions are G invariant. So you can prove on simple correlations of that. For example, the 1-point functions vanish unless you have identity, which is 1, and the 2-point functions depend. So the dependence on 2-point functions on W1 and W2 is fixed by conformal invariance to be this 1 over W1 minus W2 to the 2n, where 2n is the weight of the modular form.
So in this picture of this surface with the orbifold points, where should I see this coordinate W?
Yeah, the W doesn't live on the surface at all. It's like an auxiliary variable, which arises because you have an infinite. No, it's just a way to parameterize different functions. I don't know how to say it. Okay, maybe I could write a more explicit formula, but I mean, here's the definition of W. You start with a function which is a lowest weight vector, so this is like the primary operator, and you just act on it with a translation. So it's the W just tells you how the function is translated around G mod gamma. It's not very. It's maybe not super intuitive, yeah, from the way I defined it. But okay, yeah. Anyway, you should just think of it as an auxiliary, the parameter in a new space, which is not the space, which is not on the surface itself.
In particular, you said do the top way.
Well, it does act on it. It does act on it in the same way. It's kind of okay. You should maybe think of it as the complexification of the boundary of H2, because that's PSL. This is how PSL2R acts on local operators. So the local operators kind of sit on the boundary of H2, but more in a complexified way. Yeah. So for each hyperbolic orbifold, you can define this class of correlators. Okay, this is kind of what I was saying. The boundary of H2 kind of lives here, and this is its complexification. When they live in the, oh, sorry, maybe the boundary is more like the real is the circle. Sorry, that's the right. Okay, so we have an OPE. Let's see if I can make it past this slide. And the crucial fact is that the contribution of a given irreducible representation in the sum is completely fixed by SO2R invariance. Just like in a CFT, the OP is fixed by conformal invariance up to some OP coefficients, which are these numbers F and F twiddle. And this just comes from some kind of rigidity properties of these maps. So the space of PSO2R invariant maps from product of irreducible representations to another one is just one dimensional. And the numbers, the F's and F twiddle, they are fixed for a given surface to be these correlation functions or triple products of modular forms and the Laplace eigenvalues, Laplace eigenfunctions. And in the arithmetic cases, these things are very interesting because they are related to L functions. So,
sorry, but this will be convergence comes from here.
It just comes from the fact that it comes from the L2 theorem. I mean, the theorem which tells you that any eigenfunction, any function, any say L2 integrable function can be expanded as a convergent sum of eigenvalues.
Yes.
Yeah, that's a good question. Okay, so now we have this OPE. We can do the bootstrap. So this is what bootstrap means here, which is to impose associativity, to take the correlation function or integral of a product of 4 automorphic forms, O bar, O bar, and expanding it in 2 different ways, either using this product or this product. And you find an identity, which is this infinite sum of over Laplace eigenfunctions on one side, equal to infinite sum over modular forms on the other side. Here it is more explicitly. The contribution of a given Laplace eigenfunction is some hypergeometric 2f1, which is basically a conformal block in a 1D CFT. Here is also a 2f1, just another type of, for the CFT people, this is a conformal block, and this is more like a conformal partial wave. I think, yeah, yes. And from it, you can get an infinite number of identities satisfied by the spectrum by expanding around a special point in this chi space. So chi is like a cross ratio, And in this case, you can actually expand around the S-channel OPE, and it converges even, this is something we cannot usually do in a CFT because the T-channel doesn't converge at chi equals 0, but here it does. So you can both channels converge at the S-channel, and things become much simpler because of that, because you just get polynomials of the scaling dimension instead of some complicated functions.
So this is like a 1D CFT with delta phi equal n.
Yeah.
Okay.
Exactly, yeah.
Okay.
Delta phi is like n, but instead of the S-channel blocks, you're expanding in conformal partial waves, and the conformal partial waves have a delta which has a complex part. So on the principal series. Okay, I want to probably not go over everything, but you can formulate this as a following proposition. So suppose. What have I? This is what I've explained so far. Suppose we have some hyperbolic surface which admits a holomorphic modular form of weight 2n. So that's something you can check using the Riemann-Roch theorem whether it has it or not. And let's assume that phi's are the complete set of Laplace eigenfunctions, and define this to be the triple product. So product of holomorphic form, its conjugate, and Laplace eigen. So it's kind of the coefficient of decomposition of this product, this h bar squared, into Laplace eigenfunctions. Then what I've explained is that this set of data satisfies some nice infinite set of identities, which look like this. So it's a sum over Laplace eigenfunction with positive coefficients, some polynomial equal to some positive number. So there's a lot of positivity. And by the way, this right-hand side is called the Rankin-Cohen bracket, which is some thing you can build out of modular forms. But yeah, the crucial point is that both these coefficients here and the right-hand side are non-negative. So we know that. We don't know what their values are, and we don't know what the lambdas are, but we know this provides a lot of constraints on the lambdas. And then you can try to prove identities, but prove bounds on the lambdas out of it. And the idea is simple. For example, you can take a linear combination of two of these identities, and you'll find this identity. So, okay, so it's a sum over all of the Laplacian spectrum of some polynomial. So is it some cubic polynomial of the lambdas, which depends on n, times this positive number equal to 0. And the only way this can be satisfied is if there is at least one negative contribution. So this is the blue curve is the polynomial, then it goes to infinity, and this identity shows there has to be at least one eigenvalue in the negative region of that polynomial. Okay, and then you can. Okay, so this is an upper bound in the spectral gap, right? It tells you why is an upper bound. There has to be at least one eigenvalue here, so the lambda one is at most this upper edge. You can just compute explicitly what this upper edge is. It's this number depending on n. Okay, so does this kind of make sense so far? Okay, and now you just compare this with the experimental data. So let's just use the n. Okay, so n, let's take the minimal value n for a modular form of a given topological type. Then there are only 5 options for n. It's either 1, 2, 3, 4, 6. So for all surfaces, there's always a modular form with one of these values, 1, 2, 3, 4, or 6. And then you just look at these values, and we look at what our predicted bound is, and then we can compare it with the largest known lambda 1 for the topology. So for n1, this corresponds to some torus with the order to orbifold point. For n2, it's something else. It's some 4-punctured sphere. This is a 3-punctured spheres, and you can compute kind of numerically using solve the Laplace equation numerically, and it's pretty good. So the upper bound, this simple formula, this is predicted from the bootstrap method, gives you should be an upper bound on these values. It is, and actually it comes pretty close for all of them. Here it's 45, here it's 44.89. Okay, but of course you don't have to stop here, because here for this cubic polynomial I just used 2 out of the infinite number of spectral identities. So there's a systematic way to improve these numbers, to push them down and see how close they get to the actual experimental data. which can be done using linear programming. So okay, maybe I'll just quickly go over how to do it. So these are the spectral identities at the top, which constrain the spectrum, and linear programming relies on the proposition, which is here. So you first construct some linear combination of the identities with some yet to be determined coefficient x, which are real, and provided the x's are non-positive for all even m's, and provided Q satisfies some normalization, and provided that the Q is non-negative above lambda star, then you can use this to certify an upper bound on the spectral gap lambda 1. What's the idea? You basically just take this polynomial Q, you sum it against the Fi squared over the Laplace spectrum. Now, because the x's are because of property 1, this is non-negative, so non-positive, but because of property 3, there has to be at least one. This tells you there has to be at least one negative term, and because of property 3, it tells you that the term has to have a lambda which is less than lambda star. So okay, you can just you can believe me if you, it's a bit hard to explain, but okay. And now then the task is just to scan over the values of these x's to optimize the bounds, and this we did using SDPB, which was developed by conformal bootstrapper David Simmons-Duffin. And here are the systematically improved results, and you can see that these bootstrap upper bounds get quite close to the experimental data, 8.47 compared to 8.46, for example, for n equals 1, and for n equals 6, it's super close. It's like to 7 significant digits. So in particular, there's a corollary of this method is that every hyperbolic orbifold satisfies this upper bound on lambda 1, which is probably saturated by the 2,3, which is definitely saturated by the 237 surface. Or maybe are there any questions right now? Okay. Okay, so yeah, that's it. No, that's not it yet. Even though we are running a bit short on time. But there's a very interesting question, which is whether the bounds are sharp. Right. So is the linear programming upper bound on lambda 1 sharp when we use all of the identities, meaning is it actually exactly saturated by the 237 triangle surface? And if yes, then this linear program must be able to reconstruct the whole Laplace spectrum of this triangle. Somehow, because this is the kind of the external functional, which should know about the whole spectrum, is because all of the inequalities have to become equalities. So in particular, the Q should vanish on the whole spectrum. And we can test this by plotting the optimal Q that's coming out of the linear program. And here is the plot, and it got some zeros indeed. And the first zero is at the spectral gap of the 237 triangle, and also the higher zeros, there's some degree to vanishing point of the polynomial. They are very close to actual eigenvalues of the 237 surface that we computed numerically using some other method. So it is kind of spectacular, because the only assumption that goes into this picture is that we have a surface that admits a modular form of weight 6. That's it. And then you do some linear programming, upper bound, and you find this picture, which knows about the location of the first, second, third, fourth, and fifth eigenvalue of a particular surface that has this modular form. Okay, and to prove actual sharpness, one should try to find explicit construction of the Q. But that hasn't been done in this case, but it has been done in some other cases, which is actually related to sphere packing, and I just want to quickly review. I think there's going to be someone else speaking about sphere packing a bit later on, but maybe not about the 8-dimensional one. Anyway, so this is a question of optimality in infinite dimensional linear programs. So some similar infinite dimensional linear program can be used to prove upper bounds on sphere packing density in D dimension. That's using work of Kohn and Elkies of 2001. And what is the role? What is the spectral identities in that case? Well, it's the Poisson summation formula for lattices in D dimension. So basically, bootstrap gets replaced by the Poisson summation formula. And quite famously, Viazovska, 2016, proved the sharpness of the bound in 8 dimensions, basically by directly constructing the analog of this optimal Q. So she constructed this. Well, in that case, it's not a polynomial anymore, but it's in this case, it's also not a polynomial for m equal infinity. It's like a polynomial of degree infinity. She constructed this wavy function, this magic function or extremal functional for the Poisson summation formula of 8 dimensions.
So what do you mean by sharp?
Sharp means that it's exactly saturated by actual object. Like it's actually saturated by the surface or by an actual sphere packing. So for 8 dimensions, the sphere packing is the E8 lattice. For 24 dimensions is the Leech lattice. So also, okay, so Viazovska's method also extends to 24 dimensions where it proves optimality of the Leech lattice. Okay, so that's the story in math literature. And yeah, by the way, she recently got a Fields Medal for this proof last year. And quite remarkably, very similar linear program also features prominently in the CFT literature, where it proves an upper bound on the spectral gap. So there this is much closer to the hyperbolic bootstrap that I was talking about today. And actually, in the same year when Viazovska solved the sphere packing problem, I solved the analogous problem in 1D CFT, which was to construct this magic function or extremal functional for this CFT problem. And I didn't know about Viazovska's proof at all, but then I came to Stony Brook in 2017 or 2018, and Rastelli told me about a sphere packing problem, and we were looking for a connection. Eventually, we found it. So we actually found there's a very precise mapping between Viazovska's method and my method, both from the same year, which is some interesting modular form, such that you can take Viazovska's magic function, translate it to CFT to prove optimality in 1D CFT, or you can take my method and translate it to sphere packing and prove the optimality of the E8 lattice or the Leech lattice. So, if the history could have gone a bit differently, it would be physicists solving the sphere packing problem in principle. We were very close. Viazovska was, of course, really inside, but probably it wouldn't have taken too long to physicists to figure it out how to apply my functionals to the sphere packing. But that didn't happen. Next time, yeah. So the maybe next challenge is to prove optimality for the task of the hyperbolic orbifolds. I don't know how much. Yeah, when should I?
We started late and we had many difficulties, technical difficulties. So say 5-6 more minutes or something.
Sure. Okay.
Yeah. Is it okay?
No, it's fine. Okay, then I promised to you at the beginning to prove some bounds at a fixed genus. So here's how we did it. We basically did the bootstrap for hyperbolic surfaces. Well, at a fixed genus, the thing you get is that the number of holomorphic holomorphic 2 forms, I guess, in this case, is equal to the genus. And we can use them all of these G linear independent holomorphic 2 forms. We can use them in the bootstrap. And this is like a matrix generalization of the original linear program. You need semi-definite programming, and that's how you get these bounds at fixed genus. So n equals 1 we already saw, because there is no need for the matricity. And n equals 2, n equals 3 gives you some better bounds. So the bound has to go down as genus goes up, and it's quite closely saturated by the Bolzan surface and the Klein quartic. And finally, maybe not quite finally yet, but almost, is this picture. So the picture of what is the set of lambda ones. Yeah. So the idea to prove this picture is to kind of keep moving to the left. I already sketched this, right? We already know that there cannot be anything to the right. So now we just need to prove if it's not 2, 3, 7, there cannot be anything to the right of some point in between. And to do that, we study some more complicated associativity. Say for 2 homomorphic forms of 2 different weights, because 237 has basically weight 6 and weight 12. Oh yeah, it's written here. So for example, when you have modular form of weight 6 and weight 8, then there is an upper bound which is 23.099. So everything with these weights is to the left. So actually, there are only three options. Either N1 is 6, N2 is 8. In that case, you have an upper bound, or the orbifold is 237. In that case, we are here. Or N1 is less than or equal to 4, and in that case, we can use something that I showed earlier, which was this one. Well, in that case, the bound is like 30, so that's also good. So yeah, you end up proving that. Yeah, no, I'm not. This doesn't. It's lagging a little bit. Yes. I'm still connected. Oh yeah, there you are. Okay, so you end up proving that if you're above 30, it has to be 237. And you can kind of systematically keep going down until you hit this continuum. Then there is some subtleties with the continuum, but probably I shouldn't go into that. We finally also did 3 manifolds in a more recent paper. And there the method is very similar, but technically it's quite, so the idea is very similar, but technically it becomes quite different. Now you need to use representation theory of PSL2C, which is the Möbius group of the sphere, or the isometric group of the hyperbolic 3 space. Now actually there's no discrete series representation. There is only principal and complementary series, and they know about the spectrum of Laplacian, not just on functions, but also on symmetric traceless tensor fields of rank J. So now there is a kind of a spin variable from CFT, where here it measures the rank of the tensor field on which the Laplacian acts, and for each spin you have a new spectral problem. So the spectrum of a given spin is just the solving Laplace equation on these tensor fields of rank J. And here is the result. So okay, for example, here's the blue curve is an upper bound on the Laplace eigenvalue of spin 2 as a function of the Laplace eigenvalue of spin 1, and the red dots are actual hyperbolic 3 manifolds. So you can see that all of the 3 manifolds are indeed below the bound, and some of them come pretty close to the bound. The blue curve is just a universal bound. There should be no manifold above it, but it's not guaranteed that the manifold will actually kind of populate so nicely the whole region allowed by the bound. Okay, so just a summary of the talk. We derived some set of identities satisfied by the spectral data of the Laplacian in hyperbolic manifolds, and then you can use linear and symmetric programming to turn these identities into bounds on the spectral gap, lambda1, which is something that we like to do in the bootstrap. And in 2D, these bounds are often nearly sharp, and also in 3D, they are sometimes quite sharp. And this more or less allowed us to identify the set of spectral gaps, which is realized in all 2D hyperbolic orbifolds. So I have some slides on CFT, and I have some more slides on sphere packing, but I think I should just, okay, I can show you this dictionary. So first, thank you. And now, yeah, here's the dictionary if you want to know how it's related to CFTs, but no, it's likely beyond the scope of the talk. So thanks.
Question?
You showed in some step you showed that this Laplacian eigenvalue problem corresponds to the 1D CFT with some integer external dimension. So what is the correspondence when the external dimension is non-integer?
Yes.
Is there generalization or something?
Yeah, that's a good question. So let me have to answer the rest. Oh, okay. So yeah, here's the here's a spectrum that appears, right? And in principle, you can use any of them as the external operator. Or you could also use the principal series, which has non-integer dimension. There are some complex dimensions. For us, it was convenient to use the red guys as the external states.
Okay.
But for hyperbolic manifolds, the red guys don't exist. So we had to use for hyperbolic 3 manifolds, the plot that I showed at the end, we had to use the blue ones. So they are non-integer dimensions. And the equation is literally, I mean, you can actually put CFTs and hyperbolic manifolds into the same framework. It's not just analogy, but it's the same, but it's slightly different. There are some small differences to the usual bootstrap.
So at least what you have done, they are correspond to the compact Riemann surface.
So the compact Riemann surface would have a discrete spectrum on the principal series.
Because here you use the Riemann here. So I assume that you are working with the compact.
Not the Riemann. I think the Riemann-Roch theorem also applies to non-compact ones.
Okay. So really, I didn't remember it correctly.
I mean, compactness is manifested by discreteness of the blue sum, not of the red sum.
I agree.
So we can see if there are there any other questions? Please.
So regarding like rigor of bounds, so you know like this semi-definite programming is going to converge for a while. But when you give this long decimal expansion, I mean we all know the first 5 digits are going to be correct if it looks like it's converging. But what if after it's converging, maybe it jumps, it converges again some new number. So how do you know? It's truncation of the decimal expansion rigorously.
Oh yeah, it's not gonna. So as a function of truncation, it has to be monotonic, non-increasing. So it's not. I mean, it's not going to jump, but of course, it's not guaranteed. It's not guaranteed that it converges. Sorry, it's guaranteed it converges to something, but it's not guaranteed that it converges to an actual value of some particular surface, right? It could, and that actually seems to be what's happening. Yeah, I think Peter Kravchuk and his student did some more careful numerical study of this, and it looks like it won't converge even for this 237 where it's such a gap. Yeah, there seems to be a little gap. I think it actually here for these digits, the red digits is pretty much what is correct, and then if I showed you more of the digits of the bound and of this lambda 1, it wouldn't agree. Yeah, so it would not. No, it seems it. Well,
so it's not sharp in your.
Yeah, I guess. Well, we don't really. I'm still a bit optimistic, but well, Peter is telling me that it's not converging, so it's.
Maybe it jumps.
Maybe it jumps. Maybe it jumps down. Yeah.
So this lambda 1 and the largest lambda 1 was computed how?
Yeah, there are various ways you could do it. The best way probably is to use the Zelberg trace formula. That will be nice.
It can be computed to arbitrary digits.
Yeah, I don't know how the complexity scales with number of digits, but I think we can certainly compute it for like 8, 9, 10 decimal places.
So this gap it's actually there. It's not.
It's probably there. Yeah, so it's kind of a cautionary tale for conformal bootstrap. That's maybe the 3D Ising model. It won't really converge, but of course we already kind of suspect that the island for the 3D Ising model doesn't really shrink to a point anyway.
Yes.
So maybe it's a manifestation of a similar phenomenon. But
spectrum is like
yeah, and here the spectrum is a bit more tame. It's still, it's still not very regular, completely regular, but it's at least it doesn't get denser and denser. For the 3D Ising model, it kind of the density grows faster than any polynomial. Here it's controlled by the Weil law, which just tells you that's basically equidistant on average, like in GFF actually. GFF it's just gaps of 2.
I guess that's why it's called. That's why you saw it in 90
yeah, that's exactly it.
So let's continue the discussion over the topic, right? Thank you. Okay, but thanks so much for the very inspiring, nice talk.
Thank you.